DIH Lombardia, and today DIH Lombardia, Intellimec, and Inestec will explain the finding of the DIH4Taking project. That is a EU-funded project that mainly focus on the object estimation and the pose estimation for the peaking phase of electronic components. And this project propose an integrated modular perception pipeline to further leverage AI technologies in this sector and similar application fields. And we decided to realize this project since advanced robotic systems could represent an effective solution to growing needs of customization and flexibility, but there are contexts where it is not so easy to implement, such as in electronic board assembly. And so can say that to perform pick and place of electronic boards, a robot system must handle the diversity of complexity in terms of size, shape, dimension. And when there are few pieces large that not overlap, there are effective consolidated, I can say, approaches. On the other hand, when pieces are small, complex, overlapped, these approaches have certain limitation, and so activities are still carried out but by human operators. And for this reason, we decided to realize this project, and the agenda of today consists of 3 main sections. I will start introducing the current context by presenting the results of the digital maturity assessment in the electronic industry. Then Davide Pasanisi of Intellimec will describe the findings about the perception module, and then Sergio Daniel Marino by Inestec will show the result of the pick and place simulation module. To conclude, we will have answer and question section. So, digital maturity in the electronic industry. I start introducing the sample of the analysis we consider and the tool that we employ. So about the sample, we select companies that operate in electronic industry. And on the slide, you can see the most frequent ATICO code of the company assessed. So manufacturing of electronic components, manufacturing of assembled electronic boards, and manufacturing of other electrical equipment. Then the prevalence of SMEs has been, as we consider SMEs, and just 20% of the companies have more than 100 employees. And about the revenue, I can say that just that we have half of the sample that has more than 10 million euros of revenues. About the tool, I can say that we employ a tool developed by Polyme for manufacturing industry, and that analyze 8 main microprocesses that are shown in the slide: the engineering, production quality, then maintenance and logistics, but also supply chain, human resource, and then to conclude, marketing, sales, and customer care. There are smart product section and a strategical one, and I can say that these processes are evaluated in terms of technology, but also control, organization, and plan or execution. And the results range along a scale that moves from 1 to 5, where 1 represents the lowest level of digital maturity, and 5 the highest one, the highest level of technological adoption. And in the middle, there are differences among the levels that are related to integration, interoperability, and procedure standardization. And then I can say that the results are the one that you can see on the slide. So the findings reveal that more than half of the sample, so in detail 54 of the total percentage of the total, gets a digital maturity index that is between 2.50 and 3.50. So half of the companies place in the middle of the scale at an intermediate level. Then a very good output is about the fact that there is not, in the left part of the slide, any company with a digital level lower than 2. And this can be index of the fact that firms have begun to pay attention to digitalization, So starting also grasp some of the benefits that digital transition offer. And the main pain point is that just 2% of the companies, of the total companies, are placed at the highest level, so between 4.50 and 5. And this makes clear that great opportunities, possibilities, benefits are still being neglected. And according to the study we develop, the key obstacle that can limit this type of company to implement digital transition are primarily the availability of the internal resources, and then clearly there are factors such as the cost, the culture, and also the supply chain integration and interaction with partners. About the average result, I can say that the maturity index, the average maturity index is 3.15 on the right part of the slide, the last column. And here I can start from the first consideration. So it is an index higher than the Lombardy sample and also the national one measured by the network of DIH of Confindustria. And this index has been calculated by combining the degree of digitalization of the 4 dimensions of the analysis represented in the slide, so execution, technology, control, and organization. And here results moving in value moving from 3.6 to 3.24. And what does it mean? That there is a moderate definition and adoption of methodologies, so also a quite good level of collaboration among the different functions. And I can also say that analyses are quite systematic, especially we will see in some function, while ECT hardware software supporting process are not always optimized or fully integrated, but are characterized by a quite good level. And one important element is that they are all above 3. And so we move away from decision making just on experience, based just on experience. And these companies implement procedure and standards. And however, I can say that these companies have a gap in integration and interoperability that are elements typical of level 4. And to conclude this slide about the value of the dimension, I can say also that there is a high level of alignment. These values are all similar one with the other, and these represent a good balance so in the management of the process, and this is clearly a quite good element. Then dealing with the microprocesses, so the 8 microprocesses shown before, I can distinguish 2 main groups. On the left, we have on one hand quality, production, design, and engineering that are all around 3.50. And on the other end, there are also all the remaining functions that are all placed below the threshold of 3. And so a more heterogeneous situation. And this situation underscored the inclination of the companies that we analyze clearly to focus on the differentiating aspects of the products, such as the excellence of design, the quality, and also to get competitiveness also on production cost. More difficulties appear in digital innovation of other function and business processes, especially about supply chain and human resources. Then I make a brief focus of each microprocess. All the findings are deeper discussed in the study we publish on our website. And here I give just some insights. I decide to represent in green some strengths and in red some pain points of each process and function. And some graph can support the analysis. In engineering, I can start distinguish product development from process engineering. On one end, product development has a quite high level of digital maturity. This is given by significant use of data, widespread integration among various systems. So, for example, bill of materials, so BOM, and versioning are managed in dedicated environments. CAD tools are diffused. Concept validation is carried out through digital tools, and you can see this last point on the graph. On the other end, on the right, process engineering is less based and tailored with digitalization. The graph makes clear that there is a limited use of of simulation tools such as virtual commissioning, but also digital twin. And in detail, just the 18 of the total sample has at least a partial integration. So if we consider full integration or full automation, this is typical just of this 4% of the companies, so quite a low value. Then production on the left and quality on the right. If we consider production, the index is 3.40, and it comes from structured digital mature elements, including the widespread use of ERP systems, and also a proper balance between the personnel with specialized tasks and operators that have cross-functional skills. So both technological and organizational parameters among the strengths, and however, there are activities which are still managed in a traditional way. So I can talk about the fact that performance analysis and production cost evaluation is based on experience, and particularly rely exclusively on the human experience, and there are no advanced analytics tools. Then I can say that at the same time, yes, there are ERP systems, but Office is still quite diffuse. And at the same time, manufacturing execution systems, so MES, is not so frequent common between these companies. And concerning quality, so on the right, it is the process with the best digital maturity level. And this mainly emerges from good performances in terms of control and organization. Control activities are performed at multiple stages, formalized procedures are employed, and so there is also a high degree of integration of quality with the other function for the identification of corrective action. And however, also in this case, some weaknesses appear, and they related this type of weaknesses to more technological aspects, including the lack of advanced, dedicated, and integrated information system for accessing, analyzing the quality data. And here I can say that the organizational structure, combining with the positive attitude to our monitoring analysis, they enable companies, this type of companies, to invest in technology, which maybe are not yet widely adopted, but that could be supported from this type of adequate structure, and so that can allow SMEs to maximize benefits also coming from digital transition. And then I move to maintenance, that is a process part of this second group of function with a lower degree of digital maturity. And here on one end in green, we have some good practice that relates with organization, with the fact that maintenance is not managed just in a reactive way, but there is preventive. But on the other hand, the weaknesses are allied in, there are multiple types of weaknesses about data management, poor digital culture, a strong prevalence of experiential approaches, and these results in a limited adoption of predictive and remote maintenance. So in the graph, you can see that just 29% of the company adopt this type of policy maintenance approaches. And in addition to what I put in the slide, I can add that CMS, so computerized maintenance management systems, are only sporadically used. And so a function that have more weaknesses compared to the other, where the level of digitalization is higher. Then I talk about logistics, supply chain, and human resources. And here about logistics, main strengths can be identified in the adoption of lean approaches, so standardized method also. And however, also in this function, there are limits about the technology dimension, so the low use in this case of WMS, warehouse management system integrated with ERP. And I can also add that formalized process for the analysis, also the measure of the monitoring of technical and or the economical performance indicator, this type of procedure are not widespread. Then moving in the middle of the slide, I can talk about supply chain. And here companies face challenges in planning, implementing action, but also in integration and exchange of information with the value chain, the production and or the distribution chain. And here I can say that physical flow are not commonly tracked, and also the interaction with customer supplier is executed through traditional channels, so emails, calls, and so dedicated electronic connection is not present. Then some good findings also in this function, but even if not yet optimal, so for example, vendor rating and rolling plan to support forecast. HR on the right here, even if some good attitude is highlighted, I want to focus on the weakness because I think that they are crucial. There are structural limitations mainly coming from a lack of formalized role and leadership teams for digital transformation. And I can say that there is also a common lack of digital skills mapping, upskilling or reskilling programs are not tailored to operative. And so I can say that there are cultural limits that can be relevant, and it's important to highlight. Then moving to the last macro process describe marketing, sales, and customer care. Here I can distinguish these three types of function. And about marketing, I can say that there is a great attention on brand presentation, common online availability of the information about also, for example, the catalog and so on. And regarding sales, according to the model, the main element to underscore is the digital sales platform. And here there is an absence, a lack of digital sales platform, e-commerce, and so on. And I can also highlight the use of rapid prototyping technologies that is shown in the graph. Or by the way, the interest toward this type of topic based on communication testing with of new products with customers. Then to conclude concerning customer care, I can say that here also in this case we have a use of traditional channels, so like for example of chatbot like chat. And here it is important to highlight that the customer relationship management, so CRM, are not widespread. And in some cases, not all the cases, but in some cases there is still traditional document management. So to conclude, I can say that this type of analysis show that companies operate in this type of field, so electronic industry, achieve good result in quality, engineering, production, so in some function, while in other one, weaknesses are more frequent, especially if I talk about supply chain. So both technological and cultural investment are important and critical to capture all the benefits and the competitive advantage that digitalization can generate. And so here, an increase in the level of automation can lead to a significant improvement in the performance of the companies of the sector. So I have concluded my part, and here I can leave the floor to Davide Pasanisi. That if you want to share the screen.
Yes. Can you see the screen?
Yes.
Okay. Hi everyone, I'm Davide Pasanisi and I work in the artificial intelligence field. I work for Intelimec, which is wait 1 second, the slide is not working. One second, okay, which is private research center. Private research center that operates in the manufacturing sector. And in Intelimec, we do applied research and technology transfer in the mechatronic field. And our goal is to create an ecosystem for our partners so that they can benefit from the opportunities offered by the state-of-the-art technologies. Intelimec is located at Chilometro Rosso in Lombardy, in Bergamo. And essentially, our mission, our goal, is to act as a bridge between the academic world and the industrial world, so that we can bring the theory from the academic world to practice in the industrial settings, since we do applied research. Today, I'm going to explain you the results of the DIH4Taking project, and in particular, the results regarding the perception module. So as it was stated at the beginning of this webinar, there are some electronic components that might require human intervention for the assembly. But so we wanted to address this issue, and here we are proposing an architecture in order to address this issue. Of course, if we want to automate the assembly of electronic components, we need machine vision pipeline, so a camera that can see the components, and we need a model that, starting from the picture of the components, is able to extract some important information that are necessary for the robot in order to carry out the pick and place operation. Here I will just address by the perception pipeline, and I will explain you what we did to achieve the final model. In order to detect the pieces, the electronic components that might be inside a bin in not in a sorted way, we relied on the synthetic data generation in order to develop a model that is able to detect the objects. We based our solution on a technique that is well known in the literature, which is known as domain randomization. And according to domain randomization, we create a virtual environment where the objects are placed, and we perturb this environment using abandoning the photorealism. So we perturb the environment in non-photorealistic ways in order to force the model to learn the essential features of the image. This can be done different ways, for example, by changing the object position or orientation, the object texture, the background texture, and so on. How did we create the virtual environment? We used Unity, which is a cross-platform game engine that allowed us to create the virtual environment, but also to generate automatically some metadata that is necessary for the model that we used during this project. These metadata are actually the labels, like the category, the depth information, object ID, and so on. In particular, we exploited a package that is available for Unity. It's freely available, and it is the perception package that allows to streamline the generation of the virtual environment and the generation of the synthetic images using Unity. And so we used this package to generate the images. And on the top, you can see the component that we used for this project, which is a PCB terminal block, a component that is used for the delivery of the power to the PCB itself. And on the at the bottom of the slide, you can see the example of images that have been generated by Unity. As you can see, the image is not photorealistic, but this is intended because, as I said before, we are using the domain randomization technique. And we used these images to train a neural network, and we used an open source library from Meta, which is called Detectron 2. And this library provides state-of-the-art detection and segmentation algorithms that have been really helpful in developing this project. We here we have the 3D image of the bin with the components, and the 3D image is composed by the depth image and the color image. We use the color image in order to detect the components that are inside the bin. As you can see at the top right, there are components that are highlighted in green, and these are the components that have been detected by the model. We leverage this information in order to segment the point cloud. And this is really helpful in order to remove the background, but also to remove the components that are not easy to pick. In fact, if you see the picture in the middle of the screen, the green components are the components that are easy to pick with respect to the others. So these are some proposals for the robotic part, and then we starting from the segmented point cloud, we calculate the pose of the object, of the components, so that we know not only the position but also the orientation. And then we provide this information to the robotic part together with the best component to pick among the ones that have been detected. And this concludes my part about the perception results.
Okay. Thank you, Davide. And now I ask Sergio to explain us the results of the pick and place simulation model. So if you want to share the screen.
Share the
Thank
screen.
you.
You can hear me, right? Can you see my screen right now?
Yes.
Okay. So, hello everyone. My name is Sergio Marinho. I'm a researcher at INESCTEC. I belong to the Center of Industrial Robotics and Intelligent Systems. And today I'll talk a bit about our development on the DIH4Taking project. More specifically, the work we've done regarding our pick and place simulation module. So starting with the index, I'll talk a bit about the main objectives of the project. Then I'll explain what the OSPS framework entails, because it is important to have a macro vision of what it is, so you can truly understand the work done on the project. Then I'll talk a bit about the main characteristics of the simulation environment that was developed, followed by the execution of an example of a pick and place operation, step by step. Then finally, I'll show you the simulation running both on a local environment and on the cloud. So the main objective of the project from our side was to build a simulated environment in Gazebo, in this case, where we are capable to test and achieve a pick and place robot mission with a final objective to pick an electronic component from a box in the simulated environment and then place them on the correct position of a PCB board. For this, we needed to integrate the perception module that Davide just presented in our robotics pipeline. Finally, we also should be able to run a large number of these simulations, both locally and on the cloud as well, with the objective of being able to test the developed pipeline in a larger scale. So starting off with the OSPS stack, it stands for Open Scalable Production System. and it is the core framework of Inestech's robotic systems. It is built on top of ROS, which stands for Robotics Operation System, and it is basically, in essence, a set of open source tools and libraries where all robotic systems can be built upon. So OSPS is a collection of modules, or ROS packages in this case, responsible for multiple things, such as the orchestration of robotic missions and the assignment of tasks inside each robot. Can also be used for robotic fleet integration and communication. So in this diagram, you can see the overall architecture of the OSPS stack, but I'll go a bit into more detail on the following slides. So starting with the concept of skills, a skill is basically a ROS package responsible for the execution of a single specific basic task. This means that each skill behavior should be something very well defined and simple. For example, we can have a skill to move a robotic arm or to capture an image from a camera, as we'll see later. These skills are composed by a client and a server, and the client requests the execution to the server by sending a goal, and then the server executes this request and it sends feedback to the client during execution, and it finishes with a certain result. Also, depending on the result, we can have different outcomes of the skill, which will be useful on the task part, which is what I'm going to show now. So on OSPS, tasks are essentially state machines composed of the skills I mentioned right now. They are defined in an SCXML file, as you can see here on the right, where different transitions and outcomes are listed between the different states of the skills. So it is possible to build different behavior using skills as the building blocks of a task, and also using their outcomes as transition tasks on the task level. So it is possible to have complex robotic missions with practically zero code repetition. Finally, the last element of OSPS stack that I will mention today is the task manager. The task manager is basically a task orchestrator inside each robot. So in a general way, each robot will have an instance of task manager running, as well as the skill servers it needs to execute some robotic mission. So the task manager will receive a task request in the form of an SCXML file, as I've showed before, this type of file. And it will execute the same task by sending requests for each respective skill server and waiting for the result execution in the correct order. That's basically it from the OSPS side. So now I will give you the rundown of all the skills that were used and developed, because as you could see, the skills are basically the building block of our robotic framework. So we used the move arm skill for the robotic move arm movement in order to be able to pick the electronic components and transporting them around. We also developed the gripper control skill, also for the picking operation. A camera capture skill, which consists on acquiring both an RGB image and a point cloud that will be used for the perception skill. That was the skill developed by IntelliMac, and they already detailed it, but it had to be integrated with our part as well. So regarding the environment, the first step on our work was to build this simulation environment. And for this, we used the simulator Gazebo, seeing that it is the default simulator usually used by ROS systems. So we created an industrial scenario that you can see here on the image. And we spawned our mobile manipulator that you can see on the right. And it is basically composed by a mobile platform with omnidirectional driving capabilities and a universal robotic arm that is mounted on top that you can see. And also mounted on this arm, that's also a depth camera, which is capable to capture both RGB images as well as 3D data in the form of point clouds. Additionally, we also put a PCB board on one of the boxes of our mobile manipulator in order to place the electronic components there as a final goal. So another important element to the simulated environment is the box where the electronic components will be present to be picked by our robot. So for the sake of dynamism of our simulation and to see if our completed stack can give response to various positions of the electronic components, we developed a script that spawns these components randomly inside a box. And as you can see on the images, there are various examples with different configurations of objects. And you can also see that some have less objects and some have more objects. That's because we also implemented some control over the number of objects that we can spawn. So we have further dynamism on the simulation. Finally, we can also see the circuit board that I mentioned earlier, which the final objective is to place the electronic objects on the board. And as you can see, there's a little gap, a little place where the object needs to be placed on for the sake of our simulation. So now we can talk a bit about the execution of the robotic mission. On this slide, you can see the task that we built, which is that state machine that I mentioned earlier, that uses the skills that I mentioned earlier, as well as the building blocks for this execution. So we basically divided it into 3 states, macro states: the picking state, the grasping state, and the placing state. And the picking state objective is to perform the perception operation and to figure out the position of the best candidate to grasp. This using the perception module developed by IntelliMech. Then we have the grasping state, where the grasping operation happens and the electronic component is picked up from the box. And then finally, we just have to place this picked electronic component on the circuit board with this last state. So here I'll show you some videos where the whole pipeline is executing. So starting from the picking operation, the first step is to execute a move arm skill and move the arm to the correct position so that the perception pipeline can run with no problems. So we can see the arm moving next to the box with the electronic components in a way that the stereo camera is located exactly a few centimeters above the box, so it can correctly capture the components. So following that, the camera capture skill is executed. As I said before, it is responsible to capture and publish on a ROS topic both the RGB image and the 3D data in the form of a point cloud, so that can be used by the perception skill on the next step. So looking at the images, we have an example of components configuration. On the left, we have the 3D representation with a point cloud, and on the right, we have the 2D RGB image. Still on the picking state, finally the perception skill is executed. and it uses as input the RGB image and point cloud information I showed on the previous slide. And this skill will estimate the best grasping pose for the candidate to be picked, as Davide already explained. So on the image, you can see the result estimation pose in the form of a three-dimensional axis on top of the point cloud representation of the object. Next, we go to the grasping state. Yeah, to the grasping state. As you'll see on the video, first the gripper closes a bit using the gripper control skill in order to minimize potential collision with the box walls and other objects. And then we use the move arm skill to hover over the object to be picked, and then we lower the arm down and perform the grasping skill using the gripper control skill. Finally, we have the placing state, where it consists on transporting the picked electronic component to the correct circuit board position and to place it there. So it makes use again of the move arm skill for that, using different waypoints along the way, along its trajectory, and follows them. At the end, the arm hovers over the correct position and then lowers the object into where it needs to be placed, as we can see right now. You can also see that the speed of simulation is a bit slow. This is because every video that I showed until now was recorded while executing the simulation locally in a not so powerful machine. So the execution, as you'll see, is much faster when we execute it on the cloud. So finally, here we have a video of another execution example, but this time running on the cloud. So all the work was deployed to the cloud, more specifically to AWS RoboMaker, which is a robotics service provided by AWS that allows for the execution of simulated environments on the cloud. So as you can see on this video, it's running much faster than the videos before that were running locally. So that's a big advantage of that. And another advantage is the fact that AWS RoboMaker supports the execution of multiple simultaneous simulations, meaning that we can execute more than one simulation at the same time. We could execute dozens or hundreds of simulations at the same time with different spawned objects on the box, and see if our pipeline can respond accordingly in these different scenarios. We still don't have concrete data about that, but preliminary tests prove that this was indeed the case, and the whole pipeline is very robust for different scenarios. That's basically it from my side. I hope you enjoyed, and if you have any questions, feel free to ask. Thanks.
Thank you. Thank you, Sergio. So if there are questions from the audience, we are here to answer. Okay. There is a question, I think.
Yes, thank you for the presentation. And a question from my side. Which are the necessary steps that we can foresee in the future to move to a potential realization of this approach, and how to communicate that to the company that maybe in the future will be interested in experimenting a real prototype, a real functioning prototype of this technology?
Well, I think that regarding the perception pipeline, the methodology is quite flexible because you just need the CAD model of the components you want to pick. Whereas regarding the robotic part, I will let Sergio answer, but I think that he might comment on the necessity to choose the right gripper.
Yeah, in simulation, obviously the objects are not as fragile as they would be in a real scenario. So we used a gripper without, without this necessity. But I would say if we wanted to try to use this work and this whole pipeline in a real environment, I think it would be possible also from the robotic side, because every skill that I mentioned can also be executed on the real robot. And the robot that you saw on the videos that I showed is actually a simulated model of a real robot that we have on in ESCTech laboratories. So with the right gripper, I think the whole pipeline would be easily integrated in a real scenario.
Thank you. Thank you very much. Very clear.
Okay, are there other questions? Okay, I think there are not other questions. So we have concluded. I thank all the participants, the partners of the project for the intervention. I hope the result can be useful in the future to the industry and all the possible target companies. And so thank you for the participation. Have a nice afternoon.
Thank you.
Thank you.
Thank you. Bye
Bye,
bye.
everyone.
Bye bye.
Bye.